then. All right, welcome everybody to my constant velocity lab report. And this is for Physics 2211, and you're hosted by yours truly, Yuvraj Didwal. Let's get started, shall we? All right, so introduction. What is the purpose of this lab? Well, the purpose of this lab is to check whether constant velocity of an object in motion can be accurately modeled by Newton's second law, or also known as the momentum principle. Newton's second law is as follows. The net force is equal to mass times acceleration of the object in motion. All right, so if the object is moving at a constant velocity, that means there's no acceleration acting on that object. If there's no acceleration acting on an object, that means there's no force acting on the object, and thus your net force is equal to 0 newtons. If you have no force acting on your object, your position update formula can be simplified to just simply displacement is equal to velocity times time. Since we should have a constant velocity, this formula should be accurate enough to model this experiment. It should be a linear relationship between the displacement of the object and the time. All right, and so for this example, for this experiment, we are going to be modeling it out using Newton's second law and Python. Our system in this experiment shall be the marker or the object in motion, and also our surroundings will be everything else. Our initial conditions for this experiment is that the initial position of our marker will be at x is equal to 0 meters, and our initial velocity of the marker shall be at a velocity of negative 0.52 meters per second. And so our assumptions for this experiment is that the object will continue to move at a constant velocity throughout the period we are choosing to track this object, because the net force on the object is obviously 0. We are also assuming that the selected point on the object is always at the same point in every single frame. Obviously, this will not happen because we are eyeballing every single point. So there is possibility for human error. There's also other issues such as other forces acting on the object, and also our object could be being acted on a force during the time we are tracking it. All right, now we shall move on to checking out our video. In this video, we'll have a marker rolling from the right side of the screen to the left side of the screen. And as you can see, we are tracking a specific point on the marker every single frame. If we go and check our lovely results, we can see that just at a glance, we can see that it is quite the linear relationship between our displacement and the time. All right, moving on to our code for the model. Well, in our code, we've stated the ball's mass shall be 6 grams, and this is a mass we found off the internet. And we also stated that the marker's velocity shall be negative 0.49 meters per second. And this is the average velocity over the first second of the marker's travel. We picked this because there's less room for error. All right. And we also chose to use our position update formula in our while loop. And this will model out the motion of the object over the time of 1.73 seconds. And as our results can show, we've got a linear graph again. And we've also got a constant velocity of negative 0.49, which is what we should be expecting, which is perfect. If we graph both our predicted model as well as the actual result on the same graph, we can see that while our two graphs are not collinear, they are nearly collinear. And this is obviously because there's human error, there could be other forces, but it seems that our model does a pretty good job of modeling this experiment. All right, what if? So the what if question for this lab is that what if we were to change the direction of our axis? If we were to flip it. If we were to flip the axis, then what we would have is our graphs, instead of being negatively sloped or downwardly sloped, they'll be positively sloped or upwardly sloped. And our position results would be in positive instead of negative. And our what does it mean question is it possible for you to say how many forces are acting on the object to give us the net zero force? And the answer is no. There are many, many different forces acting on the object. To name a few, there's gravity, electric forces, frictional forces acting on the object at all moments of time, and they're just canceling out with each other, or the magnitude of the force is simply so trivial that it's not adding up into our model. In conclusion, the motion of the object was fairly and closely modeled by the model created from the position update formula and Newton's second law. Obviously, there were some issues such as selecting accurate points. Obviously, it will not always be super accurate, but we tried our best to make it as accurate as possible. There's also the force of friction, gravitational forces due to maybe a possible slope in the table or the building itself. And there could also not be constant velocity during the points where we are selecting points and tracking.